Please start.
So before the break, I wrote. So I said that there are these 5 independent variables and 5 relations. So you might have thought that this is over constrained. So let's try to solve these because they are not all independent. So now, being a modern student in modern times, how would you try to solve these equations? You would obviously go to Mathematica and plug it in, and then you would miss seeing the patterns. So obviously at that point of time, they didn't have computer algebra packages, so they did it by hand, and they saw if you stare at it, the first thing that you would try to do is, okay, let's say u12 is equal to v and u45 is equal to, sorry, u12 is equal to u and u45 is equal to v. And so then you would look at which equation. You would actually look at this equation u51, and the last equation is going to tell you that u51 in that case is 1 minus u times v. Once you get u51, you would go back to the first equation and then get u23 is equal to 1 minus u divided by 1 minus uv. And then you would use that equation there, the first equation in number 2, you would use that to solve for u34. u34 works out to be 1 minus v divided by 1 minus uv. And finally, so 1, 2, 3, 4, 5, and we are done. So that actually solves it. Okay. So that integrand up to that measure factor simplifies enormously. So how do we write down the measure factor? So the measure factor is fixed by demanding that this should have cyclic symmetry. Because my amplitude has cyclic symmetry, this is actually an amplitude that respects this color ordering, should have cyclic symmetry. And this one is a little harder to guess or harder to solve, but I will claim, and this you should verify easily using Mathematica, that the following choice does the job. So if you consider this as the measure factor, so then this would simply become du dv divided by 1 minus uv. This object is cyclically symmetric, which essentially means that you can show that if you now cyclically permute the indices, d12 becomes d23, 45 becomes 51, these become 1 minus u23, u51, and then this becomes, keep cyclically permuting the indices, 51 becomes u12. So all of these are actually equal to this quantity here, du dv over 1 minus uv. Okay, so that fixes the measure factor. And then you can write down explicitly what the integral is. So it looks a complicated version of this guy. So let me just write it down. So the Euler beta integral gave you gamma functions, ratio of gamma functions. So this actually looks like the following: du dv 0 to 1, both becoming 0 to 1, u to the power minus alpha 1 2 minus 1, v to the power minus alpha 4 5 minus 1, 1 minus v to the power minus alpha 3 4 minus 1. So that's the full 5-particle Veneziano amplitude. Now, in the Veneziano case, the 4-particle Veneziano case, you had an integral of this kind, and you were able to write it in terms of gamma functions. So except for the poles that the gamma functions had, it was analytic everywhere else. This integral, if you wanted a similar formula, what does it look like such that it is analytic everywhere else except at the poles? So this formula did not have a solution till last December. Okay, and this is work done by Nima, Grant Remen, and Carolina. So this actually looks like there are 6 gamma functions in the numerator, 4 in the denominator, and then there is a generalized hypergeometric function, a 6th f5. So those of you who do not know what a hypergeometric function is, don't worry, you are not going to need it. But those of you who are fond of hypergeometric functions will get all excited and learn about these 6f5, because there are lots of artistic identities that you can try and come up with. So you can just imagine that if you wanted to do this for n particles, all the integrals completely, what a mess it would be. So the final thing that I wanted to say about the 5 particles case, yeah, I think I can erase all this. Yes. Bosons, yes. Colored scalars cyclically. In the external states, there are no vector particles. Yeah, that's right. Otherwise, there'd be all kinds of indices. Yeah. If you wanted to consider just a colorless scalar, then you would take this and make it crossing symmetric by hand. And that's essentially what the actual Veneziano amplitude is, a sum of 3 terms, each of which looks like the beta function. That's the 4 tachyon scattering amplitude in string theory. So these are the U variables, and these U variables are not particularly suited for doing n particle generalizations. So in the old literature, these are called the Chan variables. And then there are these new variables which were introduced by Koba and Nielsen, which are the Z variables. So this is U, and these are Zs. So the Koba-Nielsen variables are ratios of are cross ratios. So those of you who know conformal field theory, this is a language borrowed from conformal field theory. So Zj minus Zi, Zj plus 1 minus Zi minus 1 divided by Zj minus Zi minus 1, Zj plus 1 minus Zi. So the first index I runs from 1 to n. J also runs from 1 to n. But as you can see that if you put 1 and 1 here, then that variable does not exist. When you reach n, so let's call this n. So un plus 1, because you will see that there are these plus 1s here. Un plus 1 is the same thing as u1. And I urge you to verify that these actually satisfy the duality constraint. So you can easily write a Mathematica code, at least for the 5-particle case, and you'll be able to see that these satisfy the duality constraints. So here's the homework. So this is something that I'm not going to discuss. What happens if you go to the n particle Veneziano amplitude, but then there is an explicit formula which involves in terms of that in terms of these Z variables. Okay, any questions? So the challenge before us is to come up with a way. You can think of it in the spirit of effective field theory, where we are going to only consider particles that can be seen within a certain energy scale, and we are not going to retain anything beyond that. Because that is the concept of effective field theory, to understand the physics of what is happening inside an energy scale of 10 GeV. You don't put in information about what particles at 100 TeV. So how do we do that? So that is the beginning of my second lecture. So I'm going to talk about dispersion relations. So there are various kinds of dispersion relations. So my dispersion relation is going to talk about 2-to-2 scattering amplitude. It's a function of two variables S and T. And for simplicity, I'm going to just focus on scalar scattering. This can be generalized to dispersion relations of external particles carrying spin with a bit of effort, but it can be done. So I have a function of two variables. And the idea of a dispersion relation is basically just what you would get from Cauchy's theorem. So imagine that you have a function. So now we are going to think of these variables as complex variables. So imagine that you have a function of a single variable function, complex variable. Cauchy's theorem tells you that this is going to be an integral surrounding Z. So there's a small contour surrounding Z, and there is an integral of this kind. So this is an identity. So this is your complex Z plane. This is your point Z. You start off with a small contour surrounding that. And then imagine that you had some more information about this function f. So imagine that it had poles on the real axis, or it could also be branch cuts. It could be cuts as well, so it doesn't matter. Then when you unwrap the contour, you blow this contour up, you deform the contour, you basically get a big circle that surrounds the cut or the poles. And so this integral can be deformed as something that is a line integral that is surrounding the poles or the cut, plus an arc at infinity. So this can be written as line integral plus arc at infinity. If your function had a good behavior such that your arc at infinity goes to 0, then you basically get a formula for this function. You can recreate this function by just knowing the discontinuity across the poles or the cuts. Is that clear? So you can, let's work out a trivial example. So the trivial example, unfortunately, is okay. So the example is, let's say the function actually behaved like 1 over z minus 1. So now the trivial example is also going to go show you a subtlety. So in order to use this, you're going to write this as 1 over 2 pi I 1 over z prime minus 1 z prime minus z dz. So that's your original integral. And now you're going to unwrap it and pick out the continuation of a small contribution of a smaller circle that is surrounding the pole. So this is going to be equal to basically the pole that you get when you pick up the contribution from here. So this is simply going to be equal to, again, this is a trivial example, z minus 1. Okay. Yeah. So the idea of a dispersion relation here is similar, except that one thing is that we have to make sure that the arc at infinity dies. And the second thing is that we need to have some knowledge about where the discontinuities are. And the third thing, which is a bit more complicated, is that whatever I showed you is for a complex function of a single variable. And here we have a complex function of two variables. So the usual dispersion relation that people consider in the literature is what is called the fixed T dispersion relation. As the name gives away, you're going to write down a dispersion relation in a thinking about S as a complex variable, thinking of T as a fixed complex number. So the relation is going to be equal to, again, repeating exactly the same analysis. You're going to get a line integral, and the line integral is going to give you a contribution from the discontinuity. So I'll write down the final answer. So because we are holding S fixed, the first variable fixed, we are going to pick out the discontinuity of this function. So the discontinuity of this function, let me just write down the formula here. So the second variable is held fixed. So you'd write down something like that, provided your function has nice behavior at infinity. Otherwise, you'd have to do some more stuff. It's straightforward, but you have to add what are called subtractions. I'll discuss subtractions later on, but for now, let's assume that it has a nice behavior at infinity. So your fixed T dispersion relation takes on that form. I think it's best that we consider an example of this fixed T. So example 1, the simplest example that you can think of. What is the simplest scattering amplitude that you can think of? Give me a form. Yes. Excellent. Excellent. Yes. M of st is a constant. Yes, lambda. Do you think this is going to work here? Excellent example, because it doesn't work here because it goes to a constant at infinity. So the arcs cannot be thrown away. So you require to add subtractions. Okay. So this one actually falls into the more complicated category of dispersion relations, which are called subtracted dispersion relations. And you can actually verify that the next example, that this is the simplest. Arcs don't die. So you have to consider subtractions. I will talk about subtractions when I need them. Right now, I don't need them. But then let's continue thinking about other examples. So let's say 1 over S plus 1 over T. What do you think happens in this case? What happens in the large S limit but fixed T? It still goes to a constant. Okay, so this also has the same behavior as this. So these kind of amplitudes would still require subtractions. Okay, so for my illustrative purposes, the simplest example is actually the string theory amplitude. So let's consider the Euler beta function. So m of st is equal to gamma of minus s, gamma of minus t, gamma of minus s minus t. So here we require some properties of the gamma functions. Now, those of you who are itching to open Mathematica and take the large S fixed T limit, there is one subtlety that I need to tell you, is that before you just blindly put in Mathematica, Mathematica is going to give you something which looks like argument this one, S to the power argument this one, and then it'll look like a huge mess. And before you do that, you use a reflection identity and make the arguments positives, okay? So if you wanted to try out on Mathematica, do the following change first. So use gamma of z is gamma of z, gamma of 1 minus z is pi by sine pi z. Use this to convert all these arguments to positive, and then do the largest 60 limit. Okay, so that is an easy way of doing that. And you can actually check that in the large S fixed T. So mentally, you are thinking that, oh, wait a second, S is large and positive, let's say. Then they should have poles, and now you're worried that what does it even mean going along the real S axis? But implicitly and secretly between us, I have put an I epsilon, so I'm not really going on the real X axis. I'm off it. So it actually behaves like S to the power T. Okay. Now you can use this original dispersion relation, provided that T is sufficiently negative. So this, first of all, T has to be less than 0. Otherwise, your arc is not going to die. So if your arc dies, and if it is negative, then you can see that your starting point is going to be the amplitude divided by sigma minus s. So there is a 1 over sigma there, but that is going to make it 1 over sigma times sigma to the t. And if t is negative, it's exactly the right form for the arcs to die. Okay. So if that was too quick, just let me write it out. So m of st at the level of the dispersive integral, this is going to look like 1 over 2 pi I integral. This is surrounding some point s, sigma equal to s, and then you write down m of sigma comma t over sigma minus s d sigma. And because of the fact that this behaves like this, you're going to replace this by sigma to the power t. There is a 1 over sigma, so this actually behaves like sigma to the power t minus 1. So if t is negative, the arc at infinity is going to die. So the fixed T dispersion relation in this particular case is going to give you a valid answer provided T is negative. So let's work out the series representation that follows from fixed T. So what do we need? So we basically require to know what this object is. So how do you do that? You go to Mathematica and do a series expansion. So you have to give dollar assumptions, n element integers, and n greater than equal to 0. Okay, so that's how you do it in Mathematica. You ask Mathematica to find out the residue at s equal to n, or do a series expansion of around s equal to n. And you will see that around s equals to integer n, this is going to look like minus 1 to the power n plus 1 over n factorial, gamma of minus t, gamma of minus n minus t, s minus n. Now simplify it a little bit more. Don't blindly use this formula, because otherwise you'll see you won't realize how simple this formula is. So now again use the reflection identity. convert these into plus t and plus n. This, on using the reflection identity, becomes Pochhammer 1 plus t sub n minus s n factorial. So this is around an integer, and we have to take the contribution of all the poles along on the real axis. So you have to sum over that. So the discontinuity here, m of, let's just focus on just the denominator here. So you will, when you're calculating the discontinuity, you're going to be calculating something that looks like this. And when you simplify this, this is going to be equal to twice IE n minus s all square plus epsilon square. And in the limit, epsilon goes to 0. This actually becomes pi times delta of n minus s. So that's a useful formula to remember, that poles correspond to maybe a minus sign. I'm not very careful with signs. But basically, the discontinuity is going to be proportional to delta functions. And as a result of which, the dispersive integral or dispersive representation simplifies. So your m of st is simply an integral 1 over pi d sigma minus s, and this is a sum, n goes from 0 to infinity, a sum of delta functions with a pi, and that Pochhammer that comes from the residue, and factorial. Now you can, sorry, this becomes sigma. And now you can just blindly do the integral. And you're just going to get summation n goes to 0 to infinity 1 over n minus s 1 plus t sub n factorial. So this is a representation for the Euler beta function, and this is the derivation of the series representation that I was telling you in the first lecture, that you could have done this dodgy step where you're doing a Taylor expansion inside the integrand and integrating term by term. So this is a more rigorous derivation of the same thing. And because of the fact that there is ST symmetric, you don't have to repeat the exercise, but you can just do the fixed S dispersion relation and you'll get this formula. So the salient properties of this representation is that at each pole, say n equal to 1, I said that a Pochhammer, whenever this argument is or this index is an integer, it's a polynomial. Because it's a polynomial, this is called a mass level. At each mass level, we have a finite number of spins, because the degree of this t variable tells you how many spins there are. And the reason for that is when you actually try to think about the spin content, you're going to expand in terms of the Legendres, and the argument of the Legendre is cos theta. Cos theta, let's pretend that these are massless particles, is 1 over, so 1 plus 2t by s. So the spin is related to the degree of the t variable. Now, remember that this formula was only valid when t was negative. So how do we recover that? You can go to Mathematica, or you can actually use a nice formula, z plus a divided by gamma of z for the large z limit when a is fixed, actually goes like z to the power a. So you can do this, and the summand here behaves like n to the power minus t, sorry, plus t. sorry, t minus 1, n to the power t minus 1. So if the summand behaves, yes, if the summand behaves like n to the power t minus 1, then for t negative, the sum is going to converge and you have a valid series representation. But as expected, this sum converges when t is less than 0. So poles in T are invisible. This sum converges when S is less than 0. So this poles in S are invisible. So in neither sum can we truncate because you're not going to have any information about the poles in the other variable. Now, at this point, you would have said that look, this is supposed to be a function that is invariant under ST interchange. This series representation does not have that property. Each term does not have that property. So maybe what I need to do is take half of this series and half of that series and add them. So what do you think is going to go wrong if you did that? Let me repeat the question. So this amplitude is invariant under SNT interchange. I have a series representation which makes the poles in S manifest, the series representation in the as poles in T manifest. What is wrong if I took half of this series and half of that series and added them? Anybody? There is nothing wrong except that you see this one converges when the real part of S is less than 0. This should be real part of T is less than 0. So if I took half of 1 plus 2, this is 1 and this is 2, then this would only converge when real part of S and real part of T are both less than 0. But that's not interesting because the poles in both the variables are invisible in that representation. Okay. So poles, you don't see the poles in this representation. So if you actually check this, you will see that you will get an agreement with the gamma function provided your S and T satisfy that constraint. The other question is that suppose we just decided that, look, I'm not interested in seeing the T poles. I'm just interested in observing the S poles and observing resonances in the S channel. So I'm perfectly happy if you give me the first representation, which is the fixed T representation, series representation of the beta function. Now that also has a problem. So let me just write that out. So here the statement is, suppose you said that I'm not interested in seeing the T poles, I'm just interested in seeing the S poles. So I'm perfectly happy working in a series representation where I truncate and I'm just using the first terms. This you should actually verify in Mathematica that this representation does not capture the fixed angle behavior. The exponentially soft behavior is not captured by that representation. So very specifically, this is the exercise that you can do. You can actually take cos theta to be equal to 0.99. And let's say S, some random value. So let's say S equal to 8.3 with cos theta equal to 0.99. So that fixes the value of T. Then you will see that because I know the left-hand side, I know the answer, I can do this numerical experimentation that how many terms in the series do I need to retain to capture, say, 90% of the left-hand side. You will see that in this particular case, you require to keep at least 500 terms. And that is an absurdly bad representation, because I'm saying that I want to see the physics inside an energy scale of S equal to 10. And I'm telling you that, look, to understand that physics, you require to keep 500 terms. So that I would categorize as an absurdly bad representation. Okay. So that is the fixed T dispersion relation. So what can we do? So let's look at the amplitude again. So there is a bit that you can do using this fixed T business. So let's write that out again. Gamma of minus T, gamma of minus S over gamma of minus S minus T. And instead of keeping T fixed or S fixed, let's stare at it and observe that typically there is also a third variable that we introduce when we do 2-to-2 scattering, which is U. So let's put U equal to minus S minus T. And let's write this in the following way: gamma of minus S, gamma of S plus U over gamma of U. And let's write down a dispersion relation, a fixed U dispersion relation. So how do we write down a fixed U dispersion relation? The logic is exactly the same, except that now I'm going to hold U fixed, and I'm going to look at the poles in S. But now there are poles both at S equal to plus integer, as well as when S plus U is minus an integer. So you have to take into account two sets of poles. Okay. So take to account S equal to n poles and S plus U equals to minus n poles. So you'll get two terms in the series, two infinite series, one corresponding to, for the lack of better words, the S channel, and the other corresponding to the T channel. So let's look at how that looks like. Again, you use the same formulas that I wrote down for the beta function. So in this particular case, I'll write them out. So the absorptive part, or the discontinuity of the amplitude, is going to be a sum of delta functions n running from 0 to infinity. And this is minus 1 to the power n over n minus s n factorial, and a Pochhammer in U. And the second information that you need is when s is minus u minus n, the absorptive part in the s variable is again a sum of delta functions. But now when u plus n plus s is 0, and now you're going to see the poles in the t variable. So now notice that this actually tells me that u plus s is minus t. So this object here, u plus s, this is nothing but minus t. This object is nothing but minus t. And you get, again, the same Pochhammer. So that gives me a new representation, the fixed u. So this one was the fixed t. So this is fixed t. And now you have the fixed u. So let's write it out. So this actually looks like now you're going to see the poles in both variables, n minus s plus 1 over n minus t. Then there is a 1 over n factorial. And then when you actually use the reflection identity and simplify things, again you get a Pochhammer, and the Pochhammer is going to be 1 minus n plus s plus t n. Which one? Yeah. Yeah. I mean, you'll get a finite domain of convergence, but then once you actually pretend that u is fixed when you're doing the dispersion relation, you are allowed to replace it by your original variables. Yeah. So all that you have to care about is where this sum converges. And so here I told you that here you require real part of t is less than 0 for the convergence. And here you actually require the real part of s plus t is bigger than minus 1. No, but you see, these are different representations. So here the poles only in S is manifest. So here the poles in both T and S are manifest in a limited domain. Okay, so this is more in the spirit of quantum field theory. And this is what people used to call the dual resonance or DHS duality. Or this is also called the dual resonance. This actually makes the dual resonance hypothesis manifest. Okay, so I told you that there was some evidence, some flaky evidence from experiments where you're supposed to find an amplitude which you can expand either in terms of the S-channel poles or in terms of the T-channel poles. So if you open the old literature, you will see that people repeatedly say that the Venezian amplitude is such an example, and that it's a sacrilege to expand in terms of poles in both variables. Okay, so that's the thing that is repeatedly highlighted in the old literature. So this actually is a representation that is also there in this big fat textbook, Grashstein and Rijek, but for some enormously mysterious reason is never quoted in the string literature. Yeah. Okay. So the moral is that you have two different series representations of the amplitude. One of them which actually makes the poles only in one of the variables manifest. The other is that you have a representation which has poles in both variables manifest. And now at this point you would have said that, okay, is this representation better than this one? Now the answer is actually still no. And the reason why it is still no is that, see, the original purpose of the Venezian amplitude was to, so the total amplitude that Veneziana was interested in, so I just wrote a part of that amplitude, is actually a sum of 3 beta functions. So one of them is b minus s minus t, this one is minus t minus u, and this one is minus s minus u. So that's the total amplitude that he was interested in. And so if you wanted to use this second representation and say that, okay, this is a good series representation for the original amplitude, this will enable me to truncate and consider that as a representation. And then I can do phenomenology. I can actually maybe move the poles around. I can put an imaginary part. I can do things with this. Now, this is the total amplitude that you were interested in, but that condition actually screws it up. So this would actually demand that real part of s plus t is bigger than minus 1. This would demand that real part of t plus u is bigger than minus 1. And this would demand that the real part of s plus u is bigger than minus 1. And that will give you a very tiny domain where this representation would be valid. So that would be also of no use. So the moral of the story so far so far fixed T truncation does not work. And the failure was that the fixed angle was not captured. Fixed U does not work. Full crossing symmetry, if you want full crossing symmetry, valid only for a limited domain. Okay. But in even now, with this couple of pieces of information, there are some old statements in the literature that requires to be clarified or at least qualified. So these are folklores. That need qualification. And these folklores have never been fully qualified in the literature. So the first folklore is that the Veneziana amplitude can either be represented as sum over S channel poles or be represented or as sum over T channel poles, but not both. So this is something that you're going to see multiple times if you open the old literature, if you open the Birth of String Theory book. You just have to do Apple F or Control F, and then you find double counting. You just require to search for double counting, and you see that everybody, all the experts actually say this, but this is manifestly wrong because I already used the fixed U representation and got something that actually has poles in both channels. So I would say a conservative way of fixing this statement is may replace can by may. So that will make it almost correct. And in fact, there is a self-contradiction inside string theory itself. And that is because now we have some better understanding of string field theory. And string field theory explicit calculations, and there are two sources. This you can open Polchinski's textbook. Although he does not give explicit formulas, Polchinski, volume 1, chapter 9. And for explicit formulas, numerical formulas, no analytic expressions were given by Ashok. So there is a paper by Ashok Sen from 2019, which is going to give you a string field theory way of doing something that is reminiscent of this second expression. So let me tell you, what is the expectation from string field theory? So string field theory says that there is a representation which looks like quantum field theory, except for one big qualification. And the qualification is that you need to add contact terms. Typically, you need to add contact terms. So in order to flesh out this formula, I need to tell you what is the vertex. And depending on the vertex, you will get a set of contact terms. Because once I specify the vertex, then your form of the contact terms will be specified. And so this was for the Veneziano amplitude. So the Veneziano amplitude is an object that has got two channel symmetry, because I was considering color ordered. So it is symmetric under ST symmetric. You can make it manifestly crossing symmetric by adding things. You don't have to, but that is what people do. And then so that is sometimes referred to as a planar amplitude. And then there is a non-planar fully crossing symmetric amplitude, which goes by the name of the Virasoro-Shapiro amplitude. That has a decomposition that has the regular three channels in quantum field theory. So S plus T plus U, and again, a suitable set of contact terms. So by that, I literally mean the following, that I should be able to write this as a sum, and then I'll see the poles, T minus N, and for each N, I will be able to identify some suitable set of contact terms. And the sum should be such that this guy converges on its own, this guy converges on its own, and this guy converges on its own. It is not as if I am adding these three to cancel divergences in one or the other. Okay, so that is the kind of representation that we are looking for. Similar for the Virasoro-Shapiro. If I was able to do that, then that would have the feeling of quantum field theory. That would enable us to talk in the language of effective field theory. Otherwise, we'd go back and say that string theory is nothing like quantum field theory. So what is it that we are looking for? So in the last 5 minutes, yes. Exactly. So that's where I'm going to go next. Right now, where is string? Very good. So string, of course, historically, once you gave me the amplitude, I wrote down an integral, I got these Koba-Nielsen variables, and from the Koba-Nielsen variables, I was able to identify something that transformed under the SL2R symmetry. And the SL2R symmetry actually gave the indication that there is an underlying world sheet. Some conformal field theory is probably lurking there. Now that, of course, is a huge conceptual leap that very smart people were able to take. That gave a lot of power. And of course, we are the moral that we are taking here is that, look, string theory is beautiful, but we secretly say that whoever is a string practitioner, we just meet over drinks and then we say that, oh, isn't this cool? And then in public, we have begun to say that it's useless. So, but secretly, the secret desire of people who actually did formal courses in string theory is somehow to fix it. Okay, so that's the desire, and so you need to know, come up with some new ideas of maybe coming up with better ways to do string theory. So the picture, you see, I said that the Veneziano amplitude may either be represented in terms of sum over S, sum over T. So this is one possible representation which is motivated by string field theory. It does not rule out the fact that it also has a representation over a limited domain in terms of the poles of one channel or the other. So what is the picture that we have? We don't require to draw or know anything about string theory. You just need to know that string theory has a way of fattening up thin lines. So the Veneziano amplitude, why is it a sum over either the S channel or the T channel poles? Is because you have a picture like this. So in the thin string limit, you can think of this as this diagram. And now you stretch it out. And in the thin string limit, you can think of this as this diagram. So what is the series representation, or what is a good series representation to have? So this picture, the fact that the world sheet can be actually deformed or stretched into the S channel or stretched in a different way to give you the T channel, gives us the following expectation that there should be some elasticity parameter. I don't know what that is. Some elasticity parameter, let's call it lambda, that enables us to deform one description into another. Okay, so the representation or the better dispersion relation that we're looking at, so let's call it the stringy dispersion relation, should admit, and I'll, for the lack of better words, I will use the name an elasticity parameter, which enables us to deform one description into another. One description into another. So this is the dispersion relation that we are looking for. And why are we looking for that is because if we have the correct one, we can truncate, we can do effective field theory with it. Okay, so that is where we are heading. So we can actually examine questions about positivity of the amplitude, and it'll be basically a non-perturbative statement. So we can ask whether we can have a non-perturbative way of thinking about these amplitudes. So right now, the fixed T or fixed U does not have this deformation parameter. There is no way of doing something to deform one into another without actually referring to analytic continuation. So analytic continuation typically means that you actually know how to sum over an infinite number of poles. So we don't want to do that. We actually want to avoid doing that summation. And so that is what we are going to do next in the next lecture. Okay, I'll stop there. Yeah. Sangmin has a question, yeah.
Does the domain of convergence also depend on this elasticity parameter?
Yeah, so in fact it will. So there is going to be, so what happens is that in this particular case, in the fixed T, I had something that looked like this. So there is this elasticity parameter. So what will happen is that this T is going to get replaced by lambda. So provided your lambda is minus lambda. So you're provided your lambda is bigger than 0. It's some elasticity parameter, so it does not depend on the kinematic variables. So it converges everywhere in the kinematic variables except for the poles. Provided you choose a lambda, it could be complex, so long as it's bigger than 0. So that's what is going to happen. And in fact, searching for such a representation has its origin in looking at explicit formulas from string field theory.
Any other question?
On lambda for the amplitude?
So, okay, as a sneak peek, I'll give you the formulas so that you can stare at how beautiful they are. Okay, let me not remove them. So, yeah, so it's a nice place to actually display the formula because it's just below that. So the new formula is going to be, so a new formula for Euler beta function. So the Euler beta function is given as sum over 1 over n factorial. And now you will have poles and both the variables. So you'll have s minus n plus 1 over t minus n. And now you'll have this elasticity parameter that is going to enter n plus lambda. And then now you have a Pochhammer as well. And the Pochhammer also has a nice form. It actually looks like s plus lambda, t plus lambda over n plus lambda subscript n. So that's the formula that we're going to derive in the next lecture. I think there is a minus sign as well. Okay. So that's your expression that you're looking for. Yeah, I'll tell you why this formula actually captures everything that we're looking for.
Is this true for any lambda then, or
Yeah,
so you
so-
can just
Yeah, so
tune
it is
lambda
true
any?
as long as you choose a complex lambda
Yes.
such that it is bigger than 0.
But
real part of lambda is bigger
you
than
can choose any lambda that fulfills this constraint, and this
Yes.
is always the same.
Yes.
Okay.
So in fact, you know, if you want to play around with it, you can do the following. So this is minus s gamma of minus t gamma of minus s minus t. So you put s equal to minus half, t equal to minus half. So gamma of half is root pi. So at s equal to minus half, t equals to minus half, this actually gives you an infinitely number of new formulas for pi.
Any other question? If not, let's thank speaker again. And also let's thank all the speaker today. Is there any announce from the local? No?